Hi, my name is Brianna Johnson. I'm a master's student working with Kezia Manlove at Utah State University. I'll be talking today about the specific details of a respiratory disease event in a desert bighorn system. I'm working with the desert bighorn herd in and around Zion National Park here in southwest Utah. The current bighorn range encompasses the southeast portion of the national park, as well as cliff and canyon habitat that continues to the south and east. The habitat is not totally homogeneous, which results in 4 subunits within the population. Bighorn sheep are native to the Zion area. The original herd was extirpated by the 1950s, likely due to respiratory disease. A few animals were translocated to Zion from southern Nevada in 1973. The herd has grown steadily since the translocation. The most recent population estimate was close to 900. Animals near the center of the herd were observed coughing in July of 2018, and those individuals subsequently tested positive for Mycoplasma ovipneumoniae. Of course, respiratory disease is of enormous conservation concern for wild sheep in North America, and Mycoplasma ovipneumoniae is the primary causative agent of this disease. When it's transmitted to naive wild sheep, it contributes to polymicrobial pneumonia and typically elicits an immune response that is quite detrimental to the host. These disease events are often severe and population limiting, and we typically expect to see years of reduced recruitment as outbreaks occur in new lamb cohorts. But that's actually not what we've documented recently at Zion. Zion is a good system for studying this kind of disease event because of the high frequency and reliability of observations. There's good access to most of the bighorn habitat, and perhaps most importantly, because of the high visibility of this herd, we're able to pinpoint pretty closely when the pathogen arrived, and there has been consistent monitoring since that occurred. So there are several ways that we're attempting to quantify this disease event and progression. We look for symptoms of respiratory disease. We look for the pathogen itself. We look for evidence of the pathogen in the form of antibodies, and we're closely tracking survival and recruitment within the herd. And as I talk about this monitoring, I'll show examples of what has been reported in some other systems and use those to contrast what we've seen at Zion. A number of symptoms are relevant, and together I used to develop a symptom score for each observation. We look for coughing, nasal discharge, nose licking, head shaking, droopy ears, and lethargy. This is what the symptom scores look like. The Black Butte herd in eastern Washington has experienced years of disease and reduced recruitment. These observations are from 2013 and represent pretty closely what is expected from lambs born to infected herds. Here we see a pulse of symptoms beginning in early June, continuing for a few weeks, and then observations end when all lambs are dead by the end of July. The symptom score ranges from 1 to 5. Coughing contributes 1 to 3 points depending on severity. Nasal discharge contributes 1 point, and head shake, droopy ears, and lethargy each have the potential to contribute half a point. This is the same scoring system applied to the 2019 lamb cohort at Zion. These were the first lambs born into the herd after Mycoplasma ovipneumoniae arrived. We can see symptoms again emerging in June, continuing through the summer, and tapering off into the fall. These lambs don't experience the mortality seen in Black Butte. The initial timing and structure of these outbreaks do look sort of similar, but these lambs were not born the same time of year. Mean parturition at Zion is early March, while parturition at Black Butte happens in mid-May. So if I adjust the time axis to align parturition, we see that in 2019, the Zion lambs are symptomatic not only later in the calendar year, but substantially later in their lives. And in 2020, lambs at Zion showed almost no symptoms, even though the number of observations actually increased. And symptoms were not observed at all in lambs after late summer. Moving on from symptoms, current infection is detected with a PCR test performed primarily on nasal swabs. These results are reported in cycle threshold, which is the number of replications required in the PCR assay to amplify pathogen RNA to a detectable level. So the important takeaway here is the inverse relationship between cycle threshold and pathogen load. A higher cycle threshold means there were fewer gene copies in the original sample, while a lower cycle threshold means the target is more readily detected. So with that inverse relationship in mind, I am going to use cycle threshold as a proxy for pathogen load. This data set from the Snowstorm Mountains in northern Nevada is a good example of cycle threshold increasing through time as a herd moves toward clearing a pathogen and the pathogen load clearly decreases. Another example here is from Hardware Ranch, which was a captive population in northern Utah early in 2020. And though the observation period is brief, the Hardware Ranch sheep also show a trend towards pathogen clearance. And this is what the cycle threshold looks like at Zion. We see a really gentle downward slope here that really looks more like maintenance than clearance. We see low Mycoplasma ovipneumoniae prevalence at Zion compared to these other herds. Over these testing periods, 53% of PCR tests from Hardware Ranch came back positive, 61% were positive from the Snowstorm Mountains, and only 14% from Zion. When we look for evidence of exposure to the pathogen, we use a competitive ELISA test. This serological test measures antibody response to MOV. This is measured in % inhibition and is usually reported categorically with results of detected, indeterminate, or not detected. And going forward, I'm going to use the measured % inhibition values instead of those categorical values. Note that there's a positive relationship here. A high % inhibition is taken to indicate a more robust immune response. So back to the Snowstorm Mountains, this chronically infected herd consistently produces high % inhibition values. Here at Hardware Ranch, we see a dramatic increase in antibody response immediately after pathogen introduction, even again over that brief time period. And here's what we see at Zion. I think the important things to note here are that the antibody response in the Snowstorm Mountains is consistently quite a bit higher than at Zion, and that the response at Hardware Ranch quickly surpasses the response seen at Zion. If we remember those categorical values, Zion again has seroprevalence that is lower than in the Snowstorm or Hardware Ranch herds. We see 23% seroprevalence at Hardware Ranch, 86% seroprevalence in the Snowstorm Mountains, and only 17% seroprevalence at Zion. Here's another way to look at the serology at Zion through time. We see that MOV antibody is pretty clearly not present before 2018. Values rise in 2018, get a little bit higher in 2019. And then in the most recent testing events, we see a dramatic reduction in antibody expression, indicating waning immunity and lack of continued exposure to the pathogen. The final component of our disease surveillance here is closely monitoring survival of identifiable animals. Over the last 2 years, we've been able to confirm lambs born to 95% of collared ewes, and 83% of those lambs survived to weaning if their mothers also survived the season. So lamb survival has been steady and high in the 2 full years since pathogen introduction. Here's what the survival curve looks like for those Black Butte lambs I talked about earlier. Likewise, adult survival has been consistent over the past 3 years. Again, Black Butte for comparison. So what is causing mortality at Zion? Our collars are programmed with a 6-hour mortality delay. 30 mortalities have been investigated since MOV was discovered. Our average time from notification to investigation is just under 3 days. The vast majority of mortality is attributed to predation. When possible, we swab nasal and bronchial passages in the carcasses. And MOV was detected in only one of those 30 animals, an animal that also had pneumonia when it died. So why does this disease event look different than what we've come to expect? Of course, there are a lot of factors that can contribute. Pathogen strain can contribute. The strain at Zion seems to be related to other strains implicated with lower virulence disease. There are host factors to consider, but animals translocated out of Zion in 2017 have experienced severe disease elsewhere. Perhaps there are environmental factors at play, but there have been catastrophic pneumonia die-offs in other desert systems. So none of these things alone can explain the discrepancy we've seen. And in the process of monitoring this disease event, we've started to think about spatial dynamics and animal movement as it pertains to disease transmission and risk. We've looked at endemic patterns and thought a little bit about how the risk of foray and other ram-driven movement patterns might be incorporated into our understanding here. You might recall that I mentioned earlier that the habitat at Zion has resulted in substructuring within the herd. We talk about 4 specific subunits: Zion National Park, the Barracks, Hilldale, and Kanab. One way to quantify and visualize how animals are interacting is with a network. When applied to animals, nodes represent individuals, edges connect individuals, and the edge weight, the width of the edges, represents the strength of a connection between individuals. So in this network of U's in 2019, circles represent individual U's, and the wider edges mean those U's are more strongly associated. Here you see that the U's are clearly segregated by subunit. And there is some additional structure within some of the units. This is where we saw symptoms in lambs in 2019. The symptoms are segregated to a few closely associated U groups. Here's the U network in 2020. Again, some U's within subunits are more closely associated than others. And here's where we saw symptoms in lambs in 2020. Again, the symptoms that we did see are segregated to particular closely associated U groups. Another way to look at spatial data is with a hidden Markov model, which defines behavioral states by determining step length and turning angle between subsequent locations. Here we see how 4 behavioral states might look on the landscape. In this example, the stationary state has a low turning angle and short step length. Normal foraging has slightly longer step length, still pretty low turn angle. Distance foraging has increased step length and a higher turning angle, and foray has the longest step length and the highest turning angle. We defined 5 behavioral states at Zion, where we have a 2-hour fixed rate and can see a lot of granularity in the data. We described static local, low movement local, moderate movement local, moderate movement directed, and long movement directed behavioral states. Here's how different age rams exhibit those behavioral states. Older rams are more likely to make big foray-like movements through most of the year. We see an unsurprising increase in foray probability during rut in the upper age classes. But rams under 3 are mostly showing moderate local movement with a slightly increased probability of longer steps in the spring, almost as though they're expelled from U groups during parturition and then rejoin them during rut. To me, this indicates that the role an individual might play in disease transmission has the potential to shift seasonally and throughout an animal's lifetime. Ultimately, I think all of these factors I've talked about are important to an understanding of this disease event. I'm excited to see what else we can learn as we continue to analyze the spatial data we have, and I hope I've made a decent case for an integrated approach that includes observational, clinical, and spatial components. I have worked with and received support from the National Park Service and Utah Division of Wildlife Resources, as well as Zion's nonprofit partner. I've borrowed some data for this presentation, so I have lots of people to acknowledge and thank. And with that, thanks for your attention. I'd be happy to take any questions here if we have time, or if you prefer, you can send me an email. Thank you.